Okay, so let's move to moment of inertia. This is a very nice topic. Moment of inertia of areas. Moment of inertia. Or second moment of area. Second moment of an area. Or some people say also the moment of second order of an area. The definition of the second moment of an area or moment of inertia is equal to, let's say, integral of y squared dA. Y squared dA. What is the concept behind this? Let's do something like a figure like this, and this is the axis x, and this is the axis y. The concept of this is something that has to do, like, imagine that you want to make this area to rotate. If you want this area to rotate about the x-axis rotation like this, this is a measurement of the inertia of this figure when you are trying to rotate this figure around that axis. Maybe it's better if I put, let me put another figure. Let me put something better like this. And you will find this case in engineering a lot. If you have an idea like this. Something like this. And you have here the x-axis and the y-axis. The y-axis. If you think about this area trying to rotate about the y-axis, some rotation like this, or trying to make this area rotate around the x-axis like this, then you will be interested in the moment of inertia of the area about for rotation around x-axis. That will be this Ix equals to integral of y squared dA. Or if you want to analyze the rotation of the area about the y-axis, you will have I sub y integral of x squared dA. As you see, this moment of inertia is always a positive number because it's made of the distance, which is a square, and the area, which is a positive number always. There is no negative areas. The area is always positive. So these numbers are always positive. And you will encounter this concept of moment inertia a lot in your engineering career. If you think about this figure that I have on the board here, you can think about that the moment of inertia about the y-axis is going to be smaller than the moment of inertia about the x-axis. Because try to think about what will be your effort in order to produce rotation about the x-axis. You have to kind of move more because the area is more far away from the axis. So you have to make the movement like it's like a larger movement. If you do the rotation about the y-axis, the rotation is kind of like it's requiring less motion. Maybe let's think about now. Let's think about a strip like that. If you think about the moment of inertia about the x-axis, you have to rotate this like little. The rotation is kind of little because all the area is very close to the axis. So it's very little rotation, very little motion rotating about that little. Most of the particles that are within this area are very close to the axis. So the rotation is little. If you think about rotation about the y-axis, this is the y-axis, then the rotation is going to be larger, right? Because there are a lot of points or a lot of components of the area that are far away from the axis. So there is more movement. I have to go far from the camera in order to produce the moment of that long piece moving around an axis, instead of the other one that is just a tiny thing, everything very close to the axis. So the motion is tiny, little, right? This moment of inertia has to do some how the area is distributed around the axis. If the area is mostly very close to the axis, the inertia is going to be little. If the area is distributed very far from the axis, then the moment is there is more motion, more rotation, energy, if you want to call it. So the moment of inertia gives you an idea about the characteristics of the area, about rotation with respect to a specific axis. So the moment of inertia depends on what axis you are talking about what axis the area is willing to rotate, or you need to area to make the rotation about. That's a very important concept about that, and also to feel what is the moment of inertia. If they ask you what is sometimes you are interested on finding the largest moment of inertia of a section, then you have to feel it. You have to feel what is the best axis to find in order to locate the best moment of inertia for a specific application. That you will be using this a lot when you study the stresses on a beam, because the moment of inertia controls how the areas are distributed in order to distribute the stresses within the beam. Okay, so what we have to do here in this class is to give you guys a little idea of the concept of moment of inertia and how to calculate it for simple figures. And it's kind of similar to the centroids. Once you have the moment of inertia of simple figures, you can calculate the moment of inertia of more complex figures by using the moment of inertia of basic figures that make up the more complex figure. So let's calculate the moment of inertia of very simple figures. Let's start by the moment of inertia of a rectangle. Remember, moment of inertia is moment of inertia. Let's do this. Let's do rectangle here. Rectangle here. Rectangle. Let's do the moment of inertia with respect to this x-axis here. This is the y-axis here. And as we said, moment of inertia with respect to x-axis is equal to integral of y squared dA. So in order to make this integral, we need to find differential of area where all the elements of the differential of area are at the same distance y from the axis of rotation that we are considering. So in this case, the differential of area has to be parallel to the x-axis. This will be the differential of area. Because it's something like this y squared is like a common factor that gets out of dA, because the y is the same for all the particles that compound that differential of area. So this is the distance y. Since the differential of area is such a thin element, all the points in that differential of area have the same distance y from the x-axis. This will be dy, the thickness of the differential of area. And let's put some dimensions here. Let's see, this is A, and this is H. So we're going about talking about the rotation of this rectangle like this around x-axis. So Ix will be equal to integral from y equals 0 to y equals h of y squared dA, where dA is equal to a dy. So that will be a dy. So this will be equal to a integral of y squared dy. So a equals to A integral from 0 to h. So that will be y cubed over 3 from 0 to h. So that will be 1/3 of h cubed. This is our first moment of inertia that we found so far. So whenever you are asked a moment of inertia of a rectangle with respect to an axis that goes through one of the sides, let's put it here. You have here the axis of rotation. Let's call it x, x. This is A, this is H. Moment of inertia about axis is A, H over 3. That's our first basic figure. Very nice. That's important finding. Let's do another one. Let's calculate now the moment of inertia of this same rectangle with respect to a different axis. Let's do it now with respect to an axis that goes to the centroid. So we now have the same rectangle. Now we are going to put the axis to the center of gravity. So this is x. If this is the center of gravity, usually this axis is called x prime. And then this is y. Same thing, this is h. And this is a. So now we're gonna do the same thing. The differential of area is this little strip here with a thickness dy and is located at the y distance from the axis of rotation. So now it's basically the same thing, but we just changed the limits of integration, because now we have that the moment of inertia with respect to x prime, where prime means that it's an x that goes through the center of gravity, is equal to integral from minus h over 2 to h over 2 of y squared dA equals to integral from minus h over 2 to h over 2 of y squared dA. Differential of area will be a times dy. So this will be a integral of y squared dy, that will be y cubed over 3 from minus h over 2 to h over 2. So our moment of inertia will be 8 over 3 multiplied by h cubed over 2 times 2 times 2, 8, minus minus, so it will be plus h cubed over 2 times 2 times 2, 8. So this will be 224 h cubed. So h cubed over 24 over 12. All right. So that's the second finding. Right? Now we have two. Now we have that if you have a rectangle and you have the axis of rotation going through the center of gravity, and this is A and this is H, the moment of inertia, x prime is equal to A H cubed over 12. Nice. Now we have two basic figures in order to work with some other more complex figures. I guess we can do a triangle, same thing with respect to the base, and the triangle with respect to the center of gravity, and we will have four basic figures. Very nice tools to work more complex figures. Let's do the triangle. Let's do a very simple triangle. This is the triangle here. X, Y, The triangle will be defined by this line. So we're gonna work the moment of inertia of this triangle with respect to the x axis. First, let's establish the differential of area, dA. That will be, as we have said, a differential of area where all the elements or the components of the differential of area have the same distance from the axis of rotation. So this differential of area has all its elements at a distance y from the axis of rotation. The width of the differential of area will be this dy, and the base, the differential of area is a rectangle, which base is x, and the height is dy. Let's put some dimensions here. Let's call this b, and this h. And the moment of inertia with respect to the x-axis is equal to integral of y squared dA, where it will be integral from, let's define dA first here. dA, then, as we said, is equal to x dy. So we have to express x as a function of y. The equation of the line that defines the triangle is equal to mx plus b, where the slope is negative minus h over b x, and the b, which is the intercept with the y-axis, will be h. So from here, h over bx equals to h minus y. So x equals to b over h minus y. So then our integral will be y squared times dA. dA will be x dy. X will be b over h minus y. That's x times dy. And then we have to do this integral for y going from 0 to h, from here to here. In that way, we sweep all the elements dA that goes from the base to the total height h. That way we will get the moment of inertia of the whole area of the triangle. All right, so will be integral from 0 to h of b over h minus y dy. This should be very easy for you guys. So will be b over h y cubed over 3 minus y 4 over 4 from 0 to h. So this will be b over h 4 over 3 minus h 4 over 4. So this will be b h cubed 1/3 minus 1/4. So that will be 12 b over h 12 4 minus 3 equals to bh cubed over 12. Okay, so we have the moment of inertia of a triangle with respect to the base xx equals to bh cubed over 12, where this is b, this is h. Great. We have another one to our arsenal. Okay. Probably the next step will be to find the moment of inertia of a triangle through an axis that goes through the center of gravity. Let's do it like this, maybe it's easier like this. And you put the center of gravity here. This is the x prime, so it's an axis that goes to the center of gravity, y. This will be h, this will be b. I guess the best way to do this is to, let's drop this axis here, let's work with this x prime here. And then, if this is the center of gravity, this distance is gonna be h over 3, and this distance is gonna be 2h over 3, right? And then we have here, in this case, our differential of area will be this dy, and this distance will be b minus x, right? So our differential of area will be b minus x dy. That will be my differential of area. And the equation of our triangle, the basic shape of a straight line, which is mx plus b. So the slope is gonna be h over b. And the intercept with the y-axis will be here at minus h over 3. So that will be our equation. And then we have to express x as a function of y in order to introduce this into the differential of area. So if I have this equals to y, then x will be equals to y plus h over 3 times b over h. That will be our equation of the straight line that generates our triangle. So then our d area will be equals to b minus x, where x is b over h, y plus h over 3, right? B minus x dy. Now we need to do the integral. We want the ix prime. This means moment of inertia about an axis that goes through the center of gravity and is parallel to the base of the triangle. Integral of y squared dA. So it's equal to integral from minus h over 3 to 2h over 3 of y squared multiplied by dA, which is b minus b over h times y plus h over 3 times dy. All right. Okay, cross your fingers. Very nice. BH3, moment of inertia with respect to a centroidal axis of a triangle equals to dh cubed over 36. That's easier. Okay, well, I leave you guys this. I am too old for this. You guys are young and you guys took your calculus 101 very recently, are very minds very agile, so you guys can do it. You should get this result. This result is good. That's what it is. And that's the center of gravity, again, of a triangle with respect to an axis that goes through the center of gravity, usually called prime, center of gravity here. Base equals B, height equal H. That's what we just found. Okay, good. So we have several findings here. Well, how do we use these basic figures in order to find the moment of inertia of a more complicated figure? In order to do that, let's say we're going to find the moment of inertia of an I section of a beam. Let's say you have a beam like this, and you need to find the moment of inertia of this beam with respect to this axis here. And you already know the moment of inertia of the rectangles with respect to an axis that goes through the centroid. So we should be able to find the moment of inertia of this figure. How do you do that? In order to do that, you need to use what is called the theorem of parallel axis. Parallel axis. What is this? This is something that is going to allow you